We're very happy to have Bruce Grossan with us today. It's been a long time, actually. Hello, Bruce. It's nice to see you again after such a long time. Bruce is working at the University of California, and he's one of the founding members of the Energetic Cosmos Laboratory here in Kazakhstan. And he's been working on the setup of this beautiful telescope that you see here, that when we first met several years ago was just a dream, I think, with parts being shipped, but nothing assembled yet. And today, in fact, it's there. It's in the south of Kazakhstan. It's working. It's doing some beautiful and interesting science that Bruce will share with us. And so please write your questions in the chat if you have any. And we have two portions of seminar. The first, between 10 and 10:50 roughly, it's a more popular science talk, very accessible for all kinds of level. And then after that, at 11, we'll have a more technical talk on the same topic, but with more details and more technicalities. And if you have time and if you are interested, please feel free to stay. The link is the same. And so I leave the word to Bruce. Welcome, and thank you for being here.
Thank you, Daniela, for that great introduction. And I'm very glad to be here. And I regret I can't see all of you in person, but at least I'll be communicating with you over this medium. So I'd like to talk to you about the technology of the NUTTELA-TAO telescope. Here it is, and it's here's a picture of it with the roof open and with our chief engineer Janat Maksut, who has really been absolutely critical to making all this happen and work. And the NUTTELA-TAO stands for the NU Transient Telescope at Assy-Turgen Astrophysical Observatory. And since they made a nice movie about the observatory, I'd like to show this to you. I think it gives you a good sense of what things are like being there. Please let me know if this movie plays all right. So right now we're showing you the observatory and the grounds around it. And this is a real speed of the telescope opening. You notice if you count about 1, 2, 3, 4, 5, the roof is almost completely open, and that'll be very important. I'll talk to you about that later. It's what's called a Naismith focused telescope with a 700 millimeter aperture, and that's fake speed. That's not real speed. It can't open that fast. Sorry. And if you'll look at the observatory, you'll see that the hills around it are very low, and so we get a very good view of the sky. Also, you notice in front of it that the solar panels and the antenna for satellite internet. And I think that that's about all I want to show. So I'm going to speed this up a little bit just to show you the very low hills, very good visibility around. Notice these the solar panels and the satellite internet. And I think that's all we really need to see. So I'm going to stop this. I'm going to try and start up my presentation again. And we'll see if, oh, we still have the pointer. That's very good. Okay. So yes, so the instrument that you'll see that actually makes the measurements is the burst simultaneous 3-channel imager, which I call the Beastie, which allows 3 cameras to view the sky at 3 different wavelengths. And the automated system is able to respond to alerts about gamma ray bursts in the optical in less than 8 seconds. I want to say, make sure that I don't confuse anybody. These are called gamma ray events, gamma ray bursts that we usually study, but we're measuring them in an optical with a regular optical telescope. Let's see. Okay. So we're talking about the ATO, or Assy-Turgen Astrophysical Observatory, which is very near Almaty in the mountains, about an hour away. The observatory is a real observatory. There's this smaller 1 meter telescope here. Let me see if I can try and get the pointer working again. see. Yes, good. There's the small telescope used for spectroscopy. There's a really big telescope. There's facilities for us to stay in and to have our meals. But what I want to draw attention to is the NUTTELA-TAO telescope, which is over here on the side. Before I get any further in this talk, I want to admit that this is a team effort. It's not just me who's made this telescope. Of course, our founder, George Smoot, who's a Nobel laureate in physics, is our founding director. I had the experimental program at our laboratory, the Energetic Cosmic Laboratory here at Nazarbayev University. Our ECL gamma ray postdoc is Dr. Komesh, and Janat Maksut is our automation engineer. But it's very important that I mention that other people have played really important roles. Dr. Bagadan, our university vice president of research, has been really important in helping us do all the important things in many pieces of this project. Eric Linder, who is another founder of ECL, our experimental staff, Dmitry Fedorov, and our administrators, Alia Nurmukhambatova, and Alia is our experimental person, Janelle and Guldana are our administrators. And they're really, really important in the work that they've done for us. It's also very important to recognize that Fesenkov Astrophysical Institute runs the observatory, and they've been very important, especially Maxim Krugov, and also all sorts of people around NU, particularly Oskar Sharapov is our machinist, and most of the instrument, the beastie instrument, has been built at NU. This is not something we bought. This is something we built at NU, down to making the metal plates to hold it. All right, so the Nutella is for measuring triggered transients like gamma ray bursts with optical instruments. What do I mean by a triggered transient? Well, right now, as we speak, there are several gamma ray observatories in space. They're orbiting in space over our head because you can't see gamma rays through the atmosphere. And if they see a gamma ray burst in their very wide field of view instruments, they'll get a signal that looks like this. A gamma ray burst is, well, there's nothing in the background, and then all of a sudden a bright burst of gamma rays, something very easy to trigger off of. So what do we see while this gamma ray instrument is measuring this very violent and variable light curve? Well, the light, of course, goes to our telescope, and it does emit in the optical. And if this here is the gamma ray light curve with these very sharp peaks, you'll see that we have resolved that in a very few cases, we sometimes see optical light from these bursts, and we resolved that there is also a brightly variable and very fast light curve. Now, it's hard for you to read these, but this is 60 seconds. So the whole thing is over in 60 seconds, and the optical is becoming too faint to measure in about 60 seconds. So here's the question. This is the one and only big question for me. What is the spectrum? In the gamma rays, we see these two power laws, and you'll note that there's this beautiful, many little measurements, each of them with small error bars that you can do these very detailed and very precise models with. And we have two power laws, very simple model. But in the optical, we have nothing. We just have a point, a single point. In the optical, all we do is say, well, it's bright, well, it's faint, and that's it. That's not going to get you much in terms of science, in terms of figuring out what's going on. So we have to do better. We have to figure out how to get a spectrum of these objects. Now, this is a little complicated, and I don't want you to get too hung up on it. I just want you to see that scientists have been taking many years to figure out that this is what they want to see. This is what they expect to see. This is the theory. The shape in the gamma ray is just two power laws. Well, there's actually many ways you can make that in nature. We really don't know what process makes these gamma ray bursts, but we do know that the optical slopes will tell us whether we're right or not. Theory says that the optical slope of this part of the spectrum can only be a slope of 1/3 or the same as you measure here in the X-rays. Over here at this lower energy, it can only be a slope of 5/2 or 2. If you measure anything else, the theory is nonsense. It's wrong. So what if the measurements don't agree with the theory? Is my experiment worthless? Not at all. If it's not the same, we've discovered some kind of new physics, and that's the best, the most exciting, the most fun outcome. Gamma ray bursts are from really, really distant objects. They're from what we call in astronomy a redshift of 1 to 2, and depending on the exact details, that's 20 to 50 billion light years away. These are really, really far. We say they're the most powerful cosmic explosions, and they tend to happen in star-forming regions. But we have no idea what is the physical process that makes the light that we're seeing from these bursts, and that's why we built the Nutella, and that's why we have some unusual technology. So what do I mean by a transient telescope? Why transient? Well, in the time that I'm going to be talking in this slide, you'll see a gamma ray burst optical signal come in this little movie I have, and then it'll go away because they're so fast. So this is all about, we need a very fast responding system, something that can make a complete measurement in something like 60 seconds. These objects are discovered in the gamma rays, but the optical adds more information to understand the physics. But making these measurements quickly is very challenging, and we need to have some technology for that. So the first thing we need is an automated response. Those gamma ray burst instruments are orbiting around our planet, and they're looking all the time, and they could come anytime, including when people who work there are having coffee or busy or whatever. You have to have an automated response and a robotic telescope that can receive that alert and make the autonomous decision to point. So this is the SWIFT telescope. In space, you see the solar panels, you see the Earth below us. This right here, this funny, strange shaped thing, is the actual gamma ray burst detector that can localize the burst for us. So a gamma ray burst goes off, and SWIFT, in just a second or two, is able to say, oh, that's in this direction over here, because SWIFT has the very unique ability to be able to pinpoint gamma ray bursts to about 30 arc minutes. Now, if you hold your thumb out at the distance of your arm and you look at that on the sky, that's about 30 arc minutes. But SWIFT can pinpoint this to about 3. So it's about a 10th the size of your thumb, tiny, tiny part of your thumb. So SWIFT's excellent performance is what we need for our experiment to start. Here's how this works. Here's SWIFT flying around in the cosmos. Again, a gamma ray burst goes off, and SWIFT locates the gamma ray burst and the direction. It sends a little signal down to this relay satellite, TDRSS, which sends it to the ground, which sends it over the internet. And as you saw, we have a satellite antenna to get the internet. So we get that signal within just a second or two at our telescope under the best conditions. Okay, so then the system checks the conditions. That is to say, it checks if it's raining or cloudy or snowing or something like this. It checks to make sure that the burst is in a direction that's above the horizon, not somewhere below it. And then if it's right, watch this, keep your eye on this right here, then it can make the measurement. Okay, so how do you automate a telescope? Simple question. And so that's all about technology, and that's what this talk was about. So the inputs to the system are sensors, like a weather sensor, like the roof sensor, like telescope sensors, like where it's pointing, what's the mirror, whether the mirror shutter is open or closed or not, where our instrument is, and what's going on with our cameras, their position, their temperatures, their settings. Okay, so here's an example of 2 sensors which tell you what the roof opener is, what the roof is doing. Here's a sensor for weather and hardware to control. Well, we need to control the telescope, of course, where it's pointing, its focus motors, the roof motors, the mirror shutters, the cameras, and the camera's focus motors. So we have all these things that we have sensors to input, we have hardware to control. And these are our fancy roof controllers, actually. So how do you automate this complicated stuff? Now, I have to tell you that I'm not an engineer, and I don't want to spend too much time doing this. So we looked for the simplest possible way we could do this. So the system that we settle on is we have these things in this electronics box, and we have another box for our roof electronics. And we have a typical router like you would find in any laboratory or home, a logic controller, a bunch of relays, and a few other power supplies and things. And so how this works is that all these controllers can be talked to over a regular Ethernet or local area network for control by a Linux computer. It's the same kind of network you have in your home or your lab. It's not anything special. As an example, to open the roof, the computer sends a command like, device, whatever, open, and it'll go over the Ethernet through our router to the logic controller. Then the logic controller will put a little voltage on a relay here, and then it'll send juice to the motor controller, and then that'll open the roof of the telescope. Now, we've done this by using very simple techniques, and it's stuff that's really easy. It's not like the bad old days. In the bad old days, to automate anything, to turn anything on or get any information from an instrument, you had to have complicated code, drivers, cards, software. All these things were complicated. They had to all be synchronized. So that when you loaded the drivers, when you started the software, when you powered the card and the firmware, was all a problem, and it was a nightmare. Then, as I started trying to figure out how to automate these telescopes, I made a sort of discovery, was that you can buy the smartest devices with commands that look just like the commands that you type into your browser. I'm not kidding when I say this. Google, when you type it in the search window of your browser, it says, you type something like, where is No Time to Die playing in Nursery Time? Okay, where is my favorite movie playing? If you look here, you'll see that that's actually information called the URL, the Uniform Resource Locator, that goes in this bar, that just has a simple address like google.com and has a simple command like search. And then it has actually pretty simple stuff here. Where is No Time to Die playing? Blah, blah, blah. Okay, so the commands to talk to these smart devices are really simple. They're just like an internet address and a command and an argument. So as an example, here's my computer connected by LAN to my telescope. There's no cards or drivers. You just send a command over an internet. And this is literally actually the computer code command that we use to move the telescope. It looks like this. Please escape this to the system. Please give the Linux curl command, and then its address, a question mark, and then it says mount move, and then it says RA2000 is 11 hours 22:33, DEC 2000 is 88:54. These RA2000 and DEC 2000 coordinates are something that any astronomer would recognize. If you're going to use a device that's for telephony, you would put like a phone number that anyone would recognize. It's really that simple. Just pick URL smart kind of devices. And there's no special cables involved. It's just over the regular internet. So our computer program that makes the decisions on how to command everything is a little bit extensive, but there are sensors and monitors give information input, like, for example, the weather sensor talks to the parts of the program that want to be looking after the weather, making sure it's not raining and making sure we don't have to close the roof. The mirror cover controller also sends signals to us. The roof sensor sends signal to us. And we always have an alert monitor listening for those alerts from the satellite to tell us when there's a burst. So the satellite is there, a burst comes, and the transient alert monitor says, oh, there's a burst. We better do the burst thing. We better say, if, burst, then, and do stuff. So the program makes decisions like, is it raining? Is the star above the horizon, or is it below where you can't look at it? If everything's okay, then it sends a command to the output and it tells it, hey, go ahead and point at that burst. All right. Who cares? I mean, most of you must be thinking, who cares? I'm never going to automate a telescope. But I'm telling you, these devices are very simple and they're available everywhere. So specifically, you can automate your home. My printer actually has a web page already. All I did was just look in the manual, look on this little screen. It showed me what to type in my web browser, and there it was. You can control this thing using a web browser. Your home router probably almost certainly has, again, its own web page you can control things with. So there's all sorts of pieces that are this URL smart around your house already. But I happen to know that people want to sell you complicated systems to do what they call home automation. But when I looked up home automation, I found that there were 16 in this one article, free systems to do this. And I happen to know that there are espresso makers and refrigerators and washing machines that respond to actually URL-like commands that you can use and do things with yourself. So I encourage you, if you're interested in automation, try this out sometime. So now you have know all my tricks about making something robotic. I run a program on a Linux machine, but then I use very simple URL-based commands. And now we need a fast telescope so we can go and point at that gamma ray burst before it's over. So it turns out that modern telescopes are pretty fast. All the old telescopes I went to look at, they were all extremely slow and took minutes and minutes and minutes to move. But it turns out that modern small telescopes are all computer controlled, have all computer controlled digital motors, and they're very quick. And so I went to the factory of this one, and everybody count with me now. I told it to go from pointing high on the right to pointing low on the left, as far as you could possibly go around. And I timed it in 1001, 1002, 1003, 1004, 1005, 1006. So it's done in about 6 seconds, but we need to have the telescope stabilized so that it doesn't smear our images. And it turns out that the longest moves you can make with the telescope were all done in about 7 to 8 seconds. And of course, a typical move will be much faster, more like 4 to 5 seconds. And no domes. The classic telescope has a big metal dome with a shutter, and the telescope looks out the shutter. And so whenever you move the telescope, you have to move the dome to match it. It turns out that these are very slow. Some of them take several minutes to rotate. The Palomar telescope actually takes about 30 minutes to rotate all the way across the sky in this direction. So we have this nice roof that opens in a few seconds, and it doesn't have to follow the telescope. Normally, we just open the telescope at the beginning of the night and leave it there and close it if there's bad weather. If we have to close it, it can still open in time for a gamma ray burst. Okay. Now things get really tricky. And the question is, how do you make these measurements in only short exposures? Normal astronomical devices like really long exposures. That's what telescopes do. All right, here's my light curve. This is about 60 seconds, it's about a minute long. And my light curve is this optical thing doing strange, fast, jerky motions. It changes a lot, the light curves of gamma ray bursts. So if I had a long exposure, like most optical telescopes have, I would erase all this time structure and I would not find out what's really going on. If there was a different physical process here and a different physical process here, I would average together and get, well, crap. I mean, these 3 dots might be as accurate as you want in terms of an average over this time period, but they destroy the time structure in here, and so they're no good. We need something that will resolve these little peaks of structure, and we need sampling like this. So that's why it's very important for us to have a camera that's very fast and that can make these measurements. A standard astronomical camera has a CCD sensor, which is not so unlike the sensors in your camera, in your phone. And it can detect each one of these little dots here is a pixel, which is a detector, excuse me. And it can measure a few to 100,000 or so electrons. And it works like this. A particle of light, a photon, comes into that semiconductor, and it gives an electron energy. It knocks it up into a band of energy such that it is conducted and can be collected on an electrode like this. Okay, and the problem is that all electronics have a little bit of noise. CCDs have extremely, extremely low noise. They have 5 electrons, 5, that's it. And so that's incredible. But the problem is, as you get to shorter and shorter exposures, you start having only handfuls of electrons as well. And so your read noise kills your signal. But there's an interesting way around this, and that is electron multiplication. When you have an electron, if you accelerate it with an electric field into an electrode, it can have enough energy to bang out 2 electrons from the surface of that metal. And then if you do this again, you can have it make more electrons out of the surface of the next electrode, and more until you come out with a huge number of electrons. In fact, a typical electron multiplying device will come up with 5,000 or 10,000 electrons from just one. So what if you took that CCD and that pixel and you attached to it an electron multiplier, which gave you 5,000 or more electrons for just one electron in? If you put it here, when the electrons and where the electrons are collected, before the electrons are read, then the reading electrons only pop out here, where you have gazillions or thousands and thousands of electrons. And so you beat this whole problem of read noise. You beat it. So let me show you the example of what I mean. This is a 5-electron read noise signal in time, different frames, and in there is a transient. Can somebody tell me where the transient is? Well, the answer is you can't, because it's impossible, because it's swamped by noise. That's where the transient is. But now let's turn on electron multiplication like we would get in a pixel in an EM CCD, an electron multiplied CCD. That's it. Right there. You've beaten the read noise. And that's the kind of exciting technology we have that we can do using modern imaging cameras with our Nutella telescope. All right, let's see. So the next thing I want to show you is our cameras. We need to measure the spectrum, as I showed you on that previous thing, the shape, the spectral shape, by measuring those slopes. And for that, how do you measure a spectrum while a thing is changing rapidly, like our gamma ray burst or any kind of transient? Traditional astronomy uses filter bands. So that is to say, I'll put a filter in front of a camera that stretches, okay, in this case, from 430 to 500 nanometers. So it measures in this area, this range of wavelengths. It measures it and it gets an average point over that wavelength. Then you might measure in another filter and get an average point in that filter. And so in this way, we describe this curve using these 3 points. All right, so the way this, really works in real telescopes is there's a filter wheel, which has a collection of different filters, RGB and others. And of course, you shine the light from the telescope into it, and the light from the telescope contains all colors, but the filter only lets one through. And so then it hits your CCD, and then you make a measurement. The problem is that won't work for a rapidly changing source. What if your source changes its spectrum, or what if it changes its flux in between you rotating that filter wheel? Your measurement will be terrible. It'll be useless. You need to have measurements in these different filters at the same time with different cameras, but viewing the same sky. How can you do that? Are you going to build 3 separate telescopes, which will each have their own strange effects? No, you don't. We use a technology called dichroics. So these dichroics are coated pieces of glass that have the property that they reflect the bluest or shortest wavelength light at a place where you choose. So telescope light, the light comes into the camera from the telescope. All the colors are in the beam, but the shortest wavelength light is reflected off into one of our cameras, which is called the G filter. The rest of the light travels through that first dichroic here, and the shortest wavelength of that light peels off and goes into the next camera, and the longest wavelength light goes through and goes into the last camera. So that's how we get 3 colors, or these 3 points on the spectrum. So this is what the design of the instrument is. We just mount 2 dichroics in the optical path, and the light comes through, bounces off the first dichroic. It turns out that we needed a folding mirror because we didn't quite have enough room. And so that went into the first camera. The second camera bounces off the dichroic, goes in there, third camera goes straight through. This is on a platform with individual focus motors that goes on this mount, which is you're seeing right here. So this whole camera goes on the side of the telescope this way. This shiny thing you're seeing in this frame is the dichroic. And here's the first one, and here's the second one. Here's what it looks like on the actual telescope. It's this instrument here, but the cover is on right now. So let's look under the cover. And this is what it looks like when it was partially constructed. Here's the hole right here of the light coming out of the telescope, comes into this first dichroic, bounces off of it and goes into camera, goes through second camera, third camera. Here's another view. Again, this is a partially constructed camera, and there's various clips and things in here that wouldn't normally be in here. Bounces off the first dichroic. You can see the mirror here, goes into the second camera. These are the actual EM-CCD cameras. Okay. So what do we get from doing this? So we've actually been able to measure some gamma ray bursts. So if you take a look, you'll see that the gamma ray burst started kind of faint, maybe got a little brighter, it's still there, and then faded away. This was gamma ray burst 2009 15B, detected on
5 minutes.
5 minutes, thank you, perfect. On September 15th of 2020. And here I'll show you, we also detected a gamma ray burst 2010 15A, October 15th of 2020. And you can see at the beginning of our images, we did see this emission. By the way, note that there's 3 stars here in this triangle and 1 star here in this triangle, 3 stars here in this triangle, 1 star in the same. So we did see it at about 50 seconds after the burst alert, but then it was gone in our latest image. So we really do find these transients, and we really are able to follow up on them. So are we done? This is, by the way, the plotted representation of these and our light curve for 2010-15. You can see we actually have 3 complete light curves in 3 separate colors. And we can both look at the very early emission, that is really what is about this experiment, what this experiment is about, and the whole light curve over the long term. We can compare all the colors and get the spectral indices, get the slope of these spectra, and it's been very nice and been very successful. So, are we done yet? Unfortunately, we're not done yet. We do need some more bursts to get a good conclusion. We need sort of brighter ones located earlier by Swift. We need early emission that's bright and not washed out by later afterglow emission. And we've only had 3 bursts so far, and they've been in marginal weather. So we need sort of better weather so we can make better measurements. So I'm going to tell you on this in terms of big scientific results that are really gonna, really gonna rock the world, just stay tuned. It'll be a matter of time. We'll catch our burst. But until then, I can ask you, do you think the theory is going to be verified, or do you think there's going to be new physics? What's your bet? So we can just ask, what's next for technology for Nutella? And there's some pedantic things like we'd really love to replace some of our heavy cables, which are interfering with the motion of our instrument, the rotation of our instrument, by changing this electrical signal in this heavy cable to an optical signal and using optical fibers to run long fibers with no losses. This is a great thing that'll really free up our camera and make us not worry about that, and will get us long signals all the way from the telescope up here on the roof. I don't know if you can see my thing, but up on the roof, way down into the shack below to the computers. Another thing is that we'd really love to have an all-sky monitoring camera to directly measure how clear the sky is. So we could have this thing running, and then we could try and figure out where is clear on the sky at this time, maybe even trying to figure out how much signal we've lost. Maybe we can even adjust our exposures this way. Finally, we have lots and lots of software automation to do. And the first is to get a precise location by matching the star field that we see with catalogs to very exactly know where each frame is pointing. That would be very useful to us. The other thing is something called image subtraction, which is really interesting, which will help us get more sensitive measurements of changes from frame to frame. And let me show you how this works. Here's two images of a galaxy field, which look to my eye exactly the same. It turns out if you take the difference of the light in these two images, there's a supernova in it. You couldn't really see this with your eye just by looking at these images, but there is indeed a whole supernova in this. And so that's the magic of image subtraction, is you get a very sensitive difference of how things change from frame to frame. It's a little bit more than just subtracting each pixel value, because these images, these profiles of these galaxies and things change from moment to moment, depending on how the atmosphere is stable and that sort of thing. The last thing that we might try in our technology is we might try to get an infrared camera. Now, an infrared camera uses this special kind of chip called a mercury cadmium telluride sensor. And this chip makes a lot of thermal noise. So you have to put it in a cryostat. A cryostat's a fancy word for a thermos, and cool it to cryogenic temperatures, 200 degrees below zero or more. And this big heavy thing is too big and heavy to fit on our little Nutella telescope. Also, we need either a cryogen, like liquid nitrogen, we need a human to go and pour this in the cryostat all the time, or we need to have special techniques to do that. So I'm gonna stop this here, and I'm gonna hope that you come up with some questions, because I'd love to tell you more and share more about this technology with you all. Thank you very much. Oh, one more, wait. Here's my gamma ray burst.
Thank you, Bruce. It was very nice, very interesting, and very exciting. And anybody has questions, you can please write in the chat. There was one by Erik Bulan that wanted to know the gamma ray burst that you showed, how far they were. What are the distances of those observations?
So as I said in an early slide, gamma ray bursts are really far away, the standard, normal, long, what we call a long gamma ray burst. And so they are typically at a redshift of 1 to 2. And so if I remember correctly, that's at about 50 billion light years. I think I wrote the number down on the slide somewhere like here. Yeah, so it's about 20 to 50 billion light years away. So these are extremely distant objects, and they're from a time back when the universe was quite different to what we see now. And because of that, they're extremely bright objects, and we would love to use them as sort of a light, a backlight to light up the universe, because you can look at the absorption of the light from the gamma ray burst and see the imprint of all the matter between you and that very distant gamma ray burst. By the way, I should tell you that a redshift of 1 to 2 is the typical value that we see, but gamma ray bursts have been discovered almost as far away as almost anything else we know in the universe. So they've been discovered to redshifts of 6 and 7. I forget what the record is, but they're extremely distant, which is one of the exciting things about studying them.
And what about the nearest ones?
And so if you look at gamma ray bursts, you'll find that there's sort of 2 different populations that we see. One of them is, like I said, something like on the order of 60 seconds in duration. So here's time duration. So there's 100 seconds. So it's, you know, somewhere in the neighborhood of 60 seconds duration. And there's another population that seems to be more like the 1/10 of a second duration. And these are called short gamma ray bursts. And the theory is when we're able to locate them, we see that they're much closer. We see that they're redshifts of point a few, 0.1, 0.2. And so it turns out that they have a smaller energy scale. Well, why do they have a smaller energy scale? Well, the first thing you should say is, well, they're less massive. And in fact, what we believe is what we've discovered is that these are the end of the life of extremely massive stars. Sometimes you see these stars, and afterwards, much later in time, you see a supernova. So we know that these gamma ray bursts are actually from a supernova explosion that somehow accelerates and focuses relativistic matter right at the observer. And we see them so bright because they are beamed. Okay, this population here, we actually know is from 2 neutron stars that are orbiting around each other, in spiraling, and then go kaboom, and then form this special relativistic jet, which is the characteristic of gamma ray bursts. Why do we know this? That's because a few years ago, a short gamma ray burst went off, and then so did the LIGO gravitational wave detector and also the European one. And so they were able to pinpoint it and show that they found the gravitational wave signature from these 2 neutron stars in spiraling and then exploding. They were able to find the gamma ray signature from the short gamma ray burst, and then they were also able to find optical and infrared signatures of this event. So that was really exciting. And so yes, so these are fairly close by, redshift of point a few, and these are really distant, redshift from 1 to 7 or 8.
So Professor Smoot has pasted a table for the redshift Z has the time the light needs to travel, and then the actual distance that the object is in the observable universe today. So it's there in the chat.
Thank you,
In the
George.
meantime, Baurjan is asking, what exactly do we want to discover observing gamma ray burst in the optical wavelengths? Why we cannot get the same information from Swift?
Okay, so I'm going to go back to this slide, and I'm going to say that this is the theorist spectrum, and that's what they give you. And as soon as one theorist says, "I'm sure that this is it. This is my brilliant idea," another theorist said, "Well, you can make 2 power laws, the 2 power laws that we see in the gamma ray spectra, in many different ways. You can have kind of a bump that looks like this and has a power law over here. Make a bump that matches this part, or you can have many bumps that end up looking like 2 power laws." The point is that if you do have this 2 electron power laws, 2 electron population, making this kind of spectrum in the gamma rays, you must have this or a similar shape to this in the optical. So by looking at the gamma rays, you don't get the whole answer. All you get is that there are 2 power laws in kind of an empirical observation. If it's this synchrotron from 2 power laws of electrons that the theorists say it is, then indeed you must have these optical signatures. That's why we must find out the shape, that is the slope of this optical emission, and it must be fast, and it must be during the gamma ray burst.
So thank you.
By the way, I'll add one more thing. This little kink here, where this power law intersects this one, the location of that we may or may not see during our observations of gamma ray bursts, but that location, the frequency of this feature, actually tells us at what radius the emission is coming from it, how far from the center of the explosion that we are actually seeing this burst emission from. So in a sense, it allows you to kind of map the gamma ray burst, which is very exciting.
So basically we have a way to model this kind of emission theoretically, and if that model is correct, then we need to see this. But to know if this is correct, we need to look in the optical, because by looking only at the gamma rays, we cannot know. Am I right?
That's exactly right.
Then Jean Dos is asking, have you tried using grating-based spectrograph instead of dichroics to capture the whole spectrum on the optical range?
Yeah, so the answer is that is I think pretty obvious to anybody who's thought about measurements. So you can think of my measurement as a 3-channel measurement. It splits all the light that we can see into 3 channels, and a spectrograph with some kind of resolution, let's say 1,000 resolution elements, makes a 1,000-channel measurement. Okay, and then you've split the light now into 1,000 different detectors. So it's the same light, you split it now 1,000 ways. That means the signal in each channel is very, very small. And so these very short exposures with a relatively faint target is very hard to do. So you just couldn't measure much with a spectrograph. You would actually end up binning all of the channels, and it would kind of look like just a few points anyways. That's the first sort of theoretical answer. The practical answer is spectrographs, typically you need to put a target on in between the jaws of in a slit. You basically need to put that in a special location in order to observe it. So unless you know the location of the burst very, very precisely in advance, you can't use this rapid response thing. You can't use a spectrograph for a rapid response target. There's another kind of an instrument called a integrated field spectrograph, where you can sort of get the spectra of every element in a picture, but it's very, very small, very, very small field of view. And you would never be able to use it for gamma ray bursts.
And we're approaching time to close and give Bruce a little bit of rest. 2 very quick questions. Anwar is asking why the telescope was not built on the mountains around there. We see mountains in the pictures.
Oh, I think we needed an observatory, and the observatory was already built, and it was there. I think just for simplicity of logistics and supplying and building an observatory, they built it on a nice flat plain, around the mountains. If you're on the top of the very highest mountain, you worry about the weather being even worse than it is on that plateau, and various things. It is true that the best locations for observatories are on mountaintops, but actually that's only when the mountain is right next to the ocean and is in a place with really exceptional weather. So it's for Assy-Turgen, putting it on that little plateau is fine.
And there was a quick question by Kasim Khan, but I think that Pawan Kumar, hello Pawan, nice to see you again after a long time, already answered. That was how frequently they happen and why we don't see them in the Milky Way. And that's because we expect in our galaxy to have one every 10,000 years. And so we should wait a little bit longer to see one in our galaxy. And,
hello, Pawan.
Yeah. it's a weird way to see each other after, but after a long time, it's nice at least to, you know, read a message from somebody. And very quickly, Rikibulan is asking, well, this is a little bit off topic, if it's possible to take colored images of galaxies, I think.
Absolutely, they do it all the time.
Yeah.
And yeah, I mean, there's all kinds of surveys to take many color pictures of galaxies for surveys. Yeah.
Now let's give everybody a chance to rest a few minutes, and then we're back here, I think, at 11 for the second and more technical talk.
Okay, and so let me say thank you to everyone who listened, and I love the questions that were science-based. I was asked to talk about the technology mostly, but the science is what gets me the most excited. And of course, feel free to forward any questions to me. You can get my email from Professor Malafarina or others.